thanks first of all for the lovely introduction. So I have like 30 minutes and there's a lot of ground to cover. So I'll just get quickly to it, right? So now before I really begin this talk, I kind of want to focus on this slide here. I call this triangle the impossible trinity of video transcoding. And what I mean by that is whenever you think about processing videos, you can only optimize for any two of these parameters at the same time. So very simple example, right? If you want a video with high quality and high file size, you can be pretty sure that the codec complexity will be pretty high. Now, while you can optimize for two of them at the same time, the trade-off isn't quite linear. For example, if you want to bump up the quality of a video, from 50 to 70 on a scale of 1 to 100, if you keep the codec complexity constant, your size might increase by like 2x. Then going from 70 to 80, another 2x, 80 to 85, another 2x. You kind of get the gist, right? So the cost really starts ballooning super quickly towards any of the far end of these parameters. So the reason I wanted to cover this first is because over the 5 years of working in the video engineering space, the number one request I get from users is to either up the quality or reduce file sizes or both. But what I've realized is that a lot of folks don't understand what trade-offs come with it. So it's kind of good to set this as a context while we go forward with the talk. So now that's out of the way, let's talk about one important question. Why compression? Like, why do we even want to talk about video compression? I mean, we of course know about the obvious benefits, right? Higher compression, smaller file sizes, which means save storage costs, save costs when it comes to data transfers, and also I guess kind of intuitively, it makes sense that it leads to faster video streaming for your users, right? But there's something else I want to touch upon that a lot of people don't really correlate, which is that video buffering is a binary state, and I kind of want to go into what I mean by this. So what I mean is that when a video is in the playing state, it's either buffering or it's not, right? There's no in-between state. So what happens is, if you encounter a buffer state, it's very sudden and abrupt. And there are multiple studies in this space that show that users would rather prefer a slightly lower quality video than having to sit through even a single buffer event. So if you have a singular goal with respect to optimizing your videos, it would be to reduce your buffer events as much as possible. So as an example to kind of illustrate this, let's say if you have 100 users, all of them with 1.9 Mbps connection, and you have a video of 2 Mbps bitrate, every single one of your users kind of encounter at least one buffer event. And that's pretty horrible, right? But if you reduce your file size by just 5%, suddenly every single one of those 100 users don't have a single buffer event. So think of it this way, by just reducing 5% of your video file size, you suddenly have eliminated 100% of your buffers. So just having this in your mind is pretty useful because you don't want to think about compression in just its absolute numbers that you save. So if you want to do it for your own system, the best way to do it is kind of to bin your users based on what the average network sizes is. Usually what ends up happening is you will find some really cool spots where you will find that just reducing compression by a little bit is suddenly going to reduce buffer rates for a large number of your audience. Now, when it comes to compression, I mean, a lot of people obviously know about this, but I kind of want to still give a background for folks who are new. So there's two types of compressions, right? There's lossy and lossless. Lossy compression is whenever you feed some data, it compresses it, but you do lose some data in between. And it happens because a lot of this data is predictive in nature. It's not an exact thing. On the other hand, in lossless compression, anything you feed in, you get the exact same thing back when you decompress it. Now, of course, this means that lossy encodes will have smaller file sizes, but the downside is it's kind of not very ideal to use in scenarios like, let's say, encoding for text or for binary files, where every single bit's precision matters. On the other hand, if you take something like a visual or auditory media, lossy encoding works perfectly. Like, take these images, for example, right? They are the same images. The left image has been lossily encoded to the one on the right, which basically means that the pixel values on these images are essentially not the same. But still, your eyes can barely tell the difference. And the reason why this happens is because of perception. Your eyes aren't really seeing pixels the same way a computer sees it. It kind of works in a very interesting way where it interprets what it sees and uses kind of its own understanding of the context and scenarios to kind of fill in the gaps, even in case there are some errors. And that's kind of the reason why lossy encoding kind of works with audio-visual content. And I have a good example to kind of illustrate this. So our eyes essentially can only see 3 wavelengths of light, R, G, and B, which is kind of why you can light up any electronic display by simply sending it 3 values, RGB for every pixel. Right now, if you wanted to do this for a 1080p display, that's over 2 million pixels, and 3 values per pixel, that's like over 6 million values, just to light up the screen once. But here's a very neat trick that leverages perception to get down the compression. So what you want to do first is you take the total brightness of the screen, you call it Y. In case anyone's wondering why the factors for the RGB and B values are different, is because our eyes are kind of differently sensitive to different wavelengths. So here, for example, our eyes are way more sensitive to green than they are to red, than they are to blue. So once we have the Y, which is the total brightness, you have 2 more variables. One is the blue chrominescence and the red chrominescence, which essentially tell you how much blue or red is in the image, right? But yeah, of course, I mean, at this point, you'll be asking me, what's the point of this, right? You started with RG and B values. You still have 3 variables, right? And that's kind of where leveraging perception comes into play. So human eyes are actually more sensitive to brightness than they are to color. So as a consequence of this, what you can do is, when you send these pixel values to your screen, instead of sending the YUV values to every single pixel, what you can actually do is send the Y value to all pixels, but send the UNV values once every 4 pixels. And it turns out that your eyes kind of can't differentiate between this a lot. So if you think about it, you're essentially saving, like reducing the data sent by half. So yeah, just wanted to kind of illustrate some example where the perception actually plays a big role when it comes to encoding, right? Here's also like a demonstration of how this kind of looks like in, if you put this on a display. So 444 is a scenario where you're sending YUV values to all pixels, and 420 is kind of the example that I talked about. So in fact, most of the videos that you encounter, in fact, almost all videos that you encounter will use 420 as a subsampling scheme these days, especially because your eyes don't get enough time between frames to even tell the difference. Now, of course, we have been kind of talking about images a lot, and we kind of have to, because at the end of the day, videos are still a bunch of images stacked one after the other, right? It's not very different from a flipbook. The only difference is that over time, we have gotten really better at coding for the temporal and the spatial differences between these frames. Now, a really good way to kind of design a good video compression algorithm is to kind of take care of these 3 fundamental things. One, you want to compress individual frames very well, then efficiently describe the changes between frames, and then test the limits of human perception. Now, one is kind of self-explanatory, right? Considering that videos are made up of images, if you compress images better, your videos are going to be better compressed, right? The second one is kind of more interesting. So these are 2 images from 2 subsequent frames in a video. And what you can see here is that there's not much visual difference between this, right, if you inspect. And in a video, a typical video runs for like 24 frames a second. So you can imagine how fast these frames move. So it kind of stands to reason that the pixel value differences between 2 subsequent frames are very low. So here's a trick. Instead of storing all these images individually, why don't we kind of store just the pixel value changes, right? And that kind of turns out to be a pretty decent encoding strategy for videos. But there's something better that we can do. So here's another video, 2 frames from another video, taken half a second apart. So what you see here is that the only thing that really moves here is the ball. Everything else in the background stays the same. Now, of course, to encode this, we can still use the pixel difference kind of a method. But there's actually another better way to do it. So let's draw a square around this this ball and kind of create a motion vector that tells you how this ball moves over time across frames. And of course, I mean, this is not going to be exact, right? Like there are some black lines on the ball which aren't at the exact same space. Also, of course, because this square is kind of, the object is a circle that's moving, right? And you have kind of marked the square. So there's a lot of surrounding pixels that don't move alongside the same way as well. But still, overall, just looking at the image, a lot of the pixels move in this direction. So now you have another layer on top of your very simple encoding strategy, which is instead of storing all the pixel value differences separately, you kind of denote areas that move over time and describe using motion vectors where they are going and how they are moving over those frames. And these are called motion blocks. And it's kind of the building blocks for almost any kind of video encodings that you see today. And these minor pixel differences that you see, at the end, you can code them separately as inaccuracies, right? Also, how accurately you code for this motion block is precisely what defines the lossiness. Like, for example, you could do a pretty lousy job at saying where this vector goes. If you do that, your video will be more lossy. You do it more accurately, it will be less lossy. Now, also, motion blocks are one of the main reasons why you see these blocky artifacts sometimes in videos when they're heavily compressed. This is primarily because if you compress a video more, you have less bits available for this motion block estimation, which means that you have less precision that's available for the prediction itself, right? Which ends up being that you see these hard square surfaces. Now, again, these are kind of foundational blocks to video engineering, and it's like a very deep topic in itself. So I'm not going to dive any deeper into this, but I just wanted to set the context because it kind of comes into play for the things that we're going to talk ahead. So yeah, now that we have kind of talked about how compression generally works under the hood when it comes to videos, let's go back to video frames for a second. There's 3 types of video frames, your I, P, and B frames. Now your I frames, these are what we call self-contained frames. The reason I call it self-contained is because you really don't need anything else for that frame to be displayed. So they are essentially like a full image, right? There is no prediction involved there. On the other hand, you have P frames, which predict pixel values based on the frame just before it. So in this example here, you have an I frame, which is a self-contained image. Then you have a P frame, which uses the motion blocks that we just talked about and other pixel differences to account for inaccuracies. And the P block predicts the pixel values. Then the P block after it takes the values that the previous P block has predicted to predict its own values. And the chain kind of goes on, right? So yeah, but here's the thing. P blocks are still essentially predictions. And like I talked about before, you can actually decide how much lossiness you want in your motion block prediction, which essentially tells you how much compression you need, right? Now, because these are predictions, it means that the more P blocks that you have in sequence, you will start experiencing a lot of compounding degradation. And it kind of makes sense, right? Because your first P block is taken from an I frame, which is pretty pure in that sense. And the first P frame is going to add some amount of lossiness to it. Then the second P frame is actually reading from the first P frame, which already has lossiness. So you're compounding on lossiness in that sense. So this is kind of a reason why you want to insert some I frames after like an n number of P frames. Now, obviously, that n number depends on a lot of parameters, but just remember that you don't want to have just one I frame and a bunch of P frames. That just ends up being very horrible in terms of qualities. It's kind of like how you would have a repeater for an optical fiber signal, for example, over long distances. So yeah, so kind of the final composition of a video looks like this. You have an I frame, a bunch of P frames, an I frame in between, a bunch of P frames. By the way, I know I mentioned B frames as well. B frames are kind of exactly like P frames. The only difference is P frames only consider the frame preceding to it for the computation. B frames are bidirectional. They also consider the ones in the front and the back. You usually don't see B frames a lot. And the main reason for that is while B frames are really good to compress because it can predict using more data sources, but unfortunately, what it also means that for a video player that wants to start playing, let's say you reach at, let's say you want to start playing at the 5-second mark, right? It now has to compute some frames on the right side as well as on the left side. So you're actually, while you're saving space, you're actually pushing a lot more difficulty onto the codec. Yeah, perfect. So now let's kind of talk about how do you determine where to place iframes, right? So the first thing is you ideally want an iframe at the beginning of the video. Simple reason for that is as soon as the video starts, you don't want the codec to be looking around for how to decode the first frame itself. The second we just discussed, you want to put iframes between frequent intervals between a bunch of p frames. And the third is you want to put an iframe at every scene change. And I want to dive deeper into this for a bit. So every time a scene changes, there's a lot of pixel values that change at the same time, right? And none of these are because of some kind of motion. It's basically an abrupt change. For example, think about the scene change in a movie, right? And motion blocks are really horrible at capturing this scene change because there is no motion to capture, right? So if you actually end up putting a p frame in a scene change, there's just so many motion blocks, and all of these motion blocks are going to be trying to predict things lossily, depending on how much compression you want. And that's just a horrible idea, because not only are you not saving space, you're actually ending up with a lot of degradation as well. So as much as possible, you want to put an iframe at every scene change. So yeah, now we have been talking about motion so much. So let's also talk about how motion affects your encoding strategy. So videos with slow motion consumes less space. And this is kind of intuitive, right? Because less motion videos mean every subsequent frame has less changes. So which means there's less pixel differences or less motion vectors to code for, and which means less data requirements, right? So opposite for fast motion video. But here's something that might sound a little bit non-intuitive at first. So even though fast motion videos actually take larger absolute file sizes, you can compress it harder. And this comes as a result of perception. And the reason for this is when you have a slow motion video, your eyes have a lot of time to inspect the little details between frames, because there's very little changing between frames as well. So which in turn means your motion blocks predictions have to be very accurate. So you're giving it more bits to allow it to code for that. But for fast motion videos, your eyes barely have any time to see what's wrong, right? So you can get away with a lot of lossy predictions. So for a fast motion video, you can apply much aggressive compressions. Now, if your eyes did not have this kind of a perceptive property, your fast motion videos would be something like 10x more than your slow motion videos. But using this, you can kind of get it to like 2 or 3x as well. Also, it's not just motion that affects how aggressively you can compress video. There are other factors as well. For example, things like lighting. Our eyes perceive dark and light sees differently. Also, things like color combinations. And generally speaking, throughout the span of a video, like again, think a movie, the lighting conditions, color combinations, your motion, this changes very drastically throughout the video. And of course, across 2 videos, they will also be pretty drastic, right? So one of the biggest questions you want to answer about compression is, now, how do we decide how to apply compression differently within different parts of the video and across videos? So this is kind of where perception-based video quality metrics come into play. So perception-based video quality metrics assigns a quality score to a video, kind of a bit similar, different to how a computer would do it. So to kind of illustrate this example, take a look at these images. So they are taken from 2 different videos, like a frame from 2 different videos. The one on the top and one on the bottom are basically compressed differently. The bottom one is compressed less, and the top one is compressed more. So you have a metric called PSNR. PSNR basically tells you how different the signal is from the original. So in this particular example, it's kind of telling you, let's take the one on the top, right? It's telling you how the pixel values in the top image differ from the original source of that image. So the one on the top has a PSNR of 31, the one on the bottom has 34 for both of these images, and higher number means it's more similar to the original, right? But if you visually inspect it, it kind of seems like the one on the right, it's kind of worse, the compression, while the one on the left, they're kind of pretty similar. And this is an example of the kind of difference that perception brings. And the reason in this particular instance is pretty straightforward. The one on the left has so many objects, so many people's faces, that your eyes don't really know where to latch onto when looking at the inaccuracies. Whereas the one on the right, you have like these long, sharp lines and very few objects. So you just latch onto that problem faster. And then again, this kind of multiplies over a video, right? Because in the video, your frames are actually still for a lot smaller period of time. So this is kind of why we need a perceptual video quality metric, because using traditional metrics, you would never be able to say how a human would view it. So there are actually a lot of tools out there that do give you perceptual-based quality metrics, but the best one out there right now is called VMAF. It's an open source project by Netflix, and the way it works is it takes a reference video and it takes your compressed video, and you can kind of ask it to tell you how a human would perceive the quality difference. And the way they built it is that they took a bunch of videos from their Netflix libraries, took a small portion of it, compressed it with varying levels of compression, and then asked casual users to kind of rate it between 1 to 5, and then took all this data and fed it into a machine learning model. So the reason we actually need this metric is that when you optimize compression, to know if your compression is good enough, you actually need a metric to even tell you how good or bad the quality is after the compression. Right? So yeah, so far we have talked about how INP frames work and how you can have varying levels of compression and quality between different video segments, and how we can calculate these relative visual qualities of encoded videos, right? So now how do we put all of this together to create a good encoding strategy? So the first thing you want to do is pretty straightforward. You want to split your videos into chunks. Kind of makes sense, right? You split your videos into chunks, you can now parallelly process each chunk. And the best way to do this is actually to split it to iframes. And the reason that works is because, as we discussed, iframes are self-contained, right? So splitting iframes will not need you to re-encode the video. And also, you can kind of, at the end of your processing, you can kind of merge them together also without a re-encode, because again, they all start with an iframe. Also, you want to avoid re-encoding as much as possible, because every time you re-encode, video encoding is a lossy activity. So you will lose some data. So the whole goal in your pipeline should be to reduce re-encodes as much as possible for all your chunks, right? But sometimes this is not going to be possible. Like, for example, your source might have really horrible iframe placements, right? In which case, you might want to take the hit from the re-encode to fix the iframes first. Also, iframes are one of the most costly resources within a video. So as much as you can optimize iframes, the better bang for your buck that you'll get. So here are some good questions to ask yourself when deciding if you want to do this re-encoding and if you want to reset your iframes, right? So first is, if the distance between two iframes is too long, then yeah, like we discussed earlier, you want to put an iframe in between. If there's an iframe that's very close to the scene, but it's not a scene change itself, just remove it. It's not serving any purpose. It's just wasting a lot of bits. On the other hand, if there's a P frame in an iframe, you actually might want to re-encode it and force the encoder to kind of put an iframe in its place, because then you get a little more leeway when it comes to more P frames preceding it, right? And sometimes, you know, all this happens because you can't control sometimes the source of the video that you get. And a lot of times what you will see is that the video source will have iframes placed at specific durations instead of strategically being placed at scene intervals. A lot of people do this simply because it's easier, but also it kind of helps with parallel processing sometimes if you want to run it in bulk system. But either ways, if your goal is to kind of compress it the best, your ideal goal should be to reduce as much of these iframe problems as you can. But of course, consider the cost of re-encoding and the loss in data and the added compute cost and everything else as well. So yeah, so now that you have the iframe situation solved, the next thing you want to do is you want to create multiple encoding variations of the same chunks with different encoding parameters. So if you take something like FFmpeg, one of these parameters would be your CRF value, right? And then what you do is you want to test these with the original using a perception quality metric. Now, you can obviously ask, is there a system that kind of tells me out of the box what parameter works best to give me a particular quality? Unfortunately, at the moment, we don't have any metrics that are as good. There is some research being done on this space, but they still don't work very well across, like for all kind of media types. So still, this is kind of the best way to do it. Now, the number of encoding variations that you want to make per chunk is kind of a complex topic in itself, but here are some general handy rules that you can do, which is for every scene, you just want to probably check these variations for just one chunk in a scene. And then whatever parameters you get, just apply it across all the chunks in the scene. It usually works out pretty well. Also, if the quality or size metrics for your encoded variation is too far off from your desired spot, then you want to tune the parameters faster or slower as you get closer to your desired value, right? Now, another thing that you want to consider is how compression affects different video resolution. And this is kind of pretty cool. So in the beginning, we did talk about how there's the trade-off between quality and size is kind of not linear, right? But what's interesting is that the graph, if you chart between quality on bitrate, is actually completely different for different resolution encodings of the same videos as well. And a very intuitive way to kind of understand this is that if you have a video with high resolution, then, and if you give it a large number of bit rate, right, obviously it's going to be better than a video with a low resolution one, right? But what happens is, if you compress it further, the amount of bits it has to code for this motion just starts drastically reducing. Like here's an example. If a 1080p video has over 2 million pixels and a 720p video consists of around 1 million-ish pixels, right? So if you start compressing, if you start reducing the available bitrate because you're compressing more in the 1080p videos, you have to now encode for 2 million pixels in this, say, 1 Mbps, as opposed to with a 720p video where you have to encode for only 1 million pixel changes in that 10 minutes. So, so because of this, you will see that once you reduce the bitrate to a certain point, the quality starts dropping off significantly fastly. So this kind of leads to this crazy inflection points, which are areas where one kind of, the lower resolution video will actually be of a higher quality than your higher resolution video, like points around here, right? Another interesting thing in this chart is the convex hull, which kind of walks you through all the ideal points where you want your videos to be encoded at, because these are the spaces where you get the most bang for your buck. And also these metrics, this chart entirely looks very different for different types of videos. Every video will have its own convex hull, they will have its own charts, which is kind of why you do those comparisons in the first place, right? So yeah, I mean, there's a lot of stuff, more interesting stuff in video transcoding to talk about. It's very interesting to dive deeper into. So if anyone's really interested in, you know, reading more about the topic, this is one of the, probably the most amazing book out there. Yes, it says it's specifically about H.264, but the author goes through some really good insights in, you know, with respect to videos in general. So yeah, thanks everyone. That's it for now. Would love to answer any questions if anyone has anything. Yeah, please. Sorry, I can hear you a little bit.
So when you were saying about putting iframes in a video while compressing, you said that you put an iframe when the scene changes so that the next p frames can generate from that iframe. What happens if the scene change is very minimal but very materialistic? For example, your quints, right? So you're putting an ad or something, and the protagonist of the video is basically pulling out an item, which is a very small scene change, but it is the main item of the video. How do you understand that small scene change to be materialistic for the videos?
Sure. So if you want to automate this whole process of inserting iframes, like one very easy way to do is if you're using FFmpeg, for example, there are functions that tell you how much pixel changes exist between every frame. So if you run a heuristic across all the pixel changes between every frame, you will find out points where the changes are greater than a particular threshold that you want to set. So it depends on you what threshold you set, right?
But that needs a manual intervention, right?
Arvind, just 1 minute. Guys who are just moving out, can you please do it silently? Because we're having question and answer session. Thank you.
Yeah. Sorry.
Yeah. So, but that, for example, it's a very small part of the video. It needs a manual intervention to tell that, okay, this is still a good point to have an iframe, right?
So in your example, the pixel changes are still less, right?
Yes, the changes are less, but the practical usage of the iframe would be more because it's a product that you're trying to show. So I don't want a p frame at that point when the product is shown.
That actually does not matter much. And the reason I say that is even if you put a p frame, the quality isn't going to substantially degrade because your compression value will be the same, right? Like let's say if you're doing something like FFmpeg, right? Let's say you take a CRF of 25. What ends up happening though is if you put a p frame where an iframe should be, it ends up creating a large number of motion blocks, and these motion blocks end up just ballooning your size. Of course, if you just take one frame at a time, that size increase is not going to be a lot. But if you do this across for a lot of frames with differences, it's going to end up being a problem. So it's less about the quality of that point being bad, but it's more about the fact that you're wasting a lot of space that you could have gotten with an iframe. And the second thing is, again, you don't want to have too many free frames as well, right? So if you had actually replaced that with an iframe, you could have put way more p frames in a group after that as well. So generally, in your scenario, what you want to do is identify like how many pixel changes are you okay with. And this can actually be a heuristic in terms of your video. Like for example, if you have a video where generally there is a lot of pixel changes happening very fast, right? So there you want to have the threshold higher because otherwise it will start putting way too much high frames, right? So you can actually create this heuristics looking at your video itself. So high changes, you reduce your threshold, increase your threshold. Low changes, you increase your threshold.
And in Quints, did you guys have something like manual timestamps from where you see, okay, this is a point where user will be most engaged in? So from there start the compression of the, like adding the p-frames and kind of like that?
Not really, because again, like I was saying, iframes, putting iframes specifically don't increase the quality from that point, because if that was the case, if you were watching a video, you will be able to know, right? Okay, suddenly the quality increased and then it decreased. That would be really horrible, right?
Yeah.
So usually that doesn't happen. So I would just recommend putting iframes at the scene changes, because the most important part is reducing the size. So I wouldn't worry about putting it like picking a spot where you want the most quality and then trying to put in an iframe.
Thank you so much. If you have further questions, Arvind will be outside to help you guys with it. Yeah.
Thanks, everyone.